Okay, I'm going to cover a little bit more of section 5.4 and 5.5 in this video. We're talking about logarithmic functions, and here's the definition of a logarithm. Y equals log base a of x means that x equals a to the y. So we looked at using that definition here in these examples. There's a couple of problems in the book where they want you to find values of logarithms, and so I'm going to show you some calculations where we're doing that now. We'll find each value. Now, more specifically, we're going to find each value without using a calculator. So most calculators can do logarithmic calculations, but only if you're in base 10 or base E. Okay, I'll comment on that again, but a bit later here. But so just keep in mind, I'm doing these calculations by hand at the moment. So in part A, I want to find the value of log base 2 of 32. I'm going to call that number y, and we need to find y, since y is representing this value here. Once we have y, we're done. Okay, now y equals log base a of x means that x equal a to the y. I'm going to use that definition to rewrite this logarithmic equation into an exponential form. X is 32, 2 is the base, y is the power of 2, and so now I'm looking at 2 to the y equals 32. This is an exponential equation. Okay, now remember that with an exponential equation, you want to solve by trying to get the same base on both sides. We looked at that in section 5.3. I can do that here. I can get base 2 on both sides. I know that 2 to the 5th is 32, so where I see the 32, I'll rewrite that with 2 to the 5th. And now I've got base 2 on both sides. I can remove the 2's and set the powers equal, and it looks like y is 5. So log base 2 of 32, that's equal to 5. Okay, part B is a similar deal. I want to find the value of log base 3 of 1 over 27. Well, I'm going to call that y, and I'm going to apply the definition. Okay, I'm going to rewrite this equation here in logarithmic form into an exponential form. X is 1 over 27. 3 is the base, y is the power of 3, and I'm going to have 3 to the y equals 1 over 27. Okay, so now I'm in exponential form, and I want to try to get the same base on both sides here to solve for y. I can do that. I can get base 3 on both sides. 3 to the negative third power would be the same as 1 over 3 cubed, or that'd be 1 over 27. So where I see the 1 over 27, I'm going to rewrite that with 3 to the negative third power. Now I've got base 3 on both sides. I can remove the 3's and set the powers equal. So y is equal to negative 3. Note that I have a negative number coming out of the calculation. That can sometimes happen. I mentioned that in the last video. You can't take log of a negative or log of 0, but you can have a negative number coming out of the calculation. You know, we'll see that on occasion. Y is the output. The input is different. Okay. Part C, I want to find the value of log base the square root of 2 of 4. Let's call that y and apply the definition for getting this into exponential form. So 4 is my input. 4 equals, the base is root 2. Y is going to be the power of root 2. And so now I'm in exponential form. I want to get the same base on both sides here. Now the square root of 2 squared would be 2. And if I square 2, I get 4. So the square root of 2 to the 4th would be 4. And now I've got root 2 here on both sides. I can remove the base and set the powers equal, and it looks like y is 4. Okay, so log base the square root of 2 of 4, that's equal to 4. Part D, I want to find the value of log of 0.01. Now, you'll notice that there's no base here. Whenever there's no base, it's understood to be base 10. you can write the base 10 if you want, or not, it doesn't matter. Okay, but if there's no base, it actually means that you're working with base 10. So I'm going to call this expression y. 0.01 is the same as 1 over 100 if you were to rewrite that into a fractional form. Okay, so now I'm looking at y equals log base 10 of 1 over 100. Knowing that I've got base 10 here means that in the exponential form, 1 over 100, that's my input. 10 is the base I mentioned, and then y is going to be the power of 10. So 10 to the y equal 1 over 100. Now I'm in exponential form. I can get base 10 on both sides. 10 to the negative second, that's the same as 1 over 10 squared, or 1 over 100. And so now that I've got base 10, I can remove the 10s and set the power is equal. And it looks like y is equal to negative 2. Again, note that I've got a negative output here. Okay, log of 0.01, that's equal to negative 2. Now, most calculators have a log button on it. Okay, if you have the 83 or 84 model, here's the log button. Okay, so in this problem, like I could have used my calculator. I could have said log of 0.01 equals negative 2. Okay, there it is. All right, so I've got a log button. I don't have a log base 2 button. I don't have a log base 3 button. I don't have a log, when the base is 10, you could use the calculator, okay? But when you have other bases, unless it's base E, I'll talk about that shortly, you're kind of limited, okay? Now some calculators are arranged such that you can enter in the base, okay, but most of them actually aren't that way. Even the high-tech ones, you can't do special bases, okay? So something to keep in mind, the way that we're doing these problems here by hand is kind of really our only option for most calculators. Next thing I want to talk about is finding the domain of a logarithmic function. I mentioned that the overall input into a logarithm can't be 0 and it can't be a negative. So in this problem here, like in part A, I've got f of x equal log base 3 of x plus 1. Okay, I want to state the domain of f. Well, x plus 1 can't be negative and it can't be 0. So if I were to set up like a side calculation here, I would want x plus 1 to be strictly greater than 0, or x would have to be greater than negative 1. In part B, I've got f of x equal log base 4 of 4 minus x squared. Okay, so 4 minus x squared, that has to be strictly a positive value here, since I don't want log of 0 and I don't want log of a negative. So I would have to kind of do a side calculation where I solve this inequality here for x. One option that you could consider is if you let y equal 4 minus x squared, that would be a parabola that is flipped upside down and then shifted up 4 units. Okay, so I've drawn that parabola. This parabola would also intersect the x-axis at negative 2, 0, and 2, 0. Now, I want to know where y is positive. Okay, any point that would be above the x-axis means that y is positive. Any point that is below the x-axis means that y is negative, and any point on the x-axis means that y is 0. So the question here, where on the graph, where on the parabola, are we plotting a point that is above the x-axis? Well, you can see if you're between negative 2 and 2 on this picture, that point is going to be above the x-axis. So the domain of f would be the set of all x such that x is between negative 2 and 2. Okay. Notice how in these problems here the base is not relevant to anything that I'm doing. The base, we don't care what that number is, right? So it's the overall input that has to be a positive when you're finding domain. All right, the next thing that I want to talk about is what's called the natural logarithm. So here's a definition. It says if the base of the logarithmic function is e, the number e, then we call it the natural logarithmic function. For notation, we're going to write the ln of x to mean log base e of x. ln x is pretty standard notation that you'll see in all math books representing a logarithm that has base e. Okay? So instead of writing log base e of x, we just simply write ln of x. It's the same thing. Y equals log base e of x, or y equal to ln of x, same thing, means that x equal e to the y. Okay, now here's if and only if. Again, that means that I can read this beginning to end or end to beginning. So, if I had x equal e to the y, that would mean that y is equal to the ln of x. Okay. Now here's just the definition of a logarithm that I've mentioned is, what I think is the most important part of talking about logarithms. You got to know the definition. And so I've just simply stated that again, but for when the base is base e. The next thing that I'd like us to do is to graph y equals the ln of x. Okay, now in order to do that, I would want to first regraph y equals e to the x. Now we've already done that in section 5.3, but I'd like us to regraph this because it's going to play a role in how I get the graph of this logarithm here. So here's the same table that I was using back in section 5.3. If I graph y equal e to the x, of course the domain is all real numbers, and so I've selected some values for x. These, again, are the same numbers that we used in section 5.3 when we did this before. So like e to the negative second, that's 0.14. Here's negative 2.14. If x is negative 1, e to the negative first is 0.37. Here's that next point, negative 1.37, etc. Okay, so the curve is rising. Of course, it's going to be increasing rapidly after you cross the y-axis there. A feature of a exponential is that there will always be a horizontal asymptote on the graph. Okay, so the curve is going to be heading outward towards the left, but it will never get to the x-axis. In other words, you'll never have 0 coming out of the calculation in this table. Now, remember that any exponential is 1 to 1. 1 to 1 just means that the inverse is a function. Okay, inverse means that you're switching x and y. So if I have y equal e to the x, and I calculate the inverse, well, I switch x and y, that means I'll have x equal e to the y. Now, x equal e to the y means y equal the ln of x. So if I want to graph y equal the ln of x, which I do, I want to graph what would be the inverse function of y equal e to the x. Okay, I'm saying the word inverse again. Inverse is all about switching x and y. So with this graph here, I want to switch the coordinates and plot the new points. Okay, let me do that now. Negative 2.14 is now going to be at 0.14 and negative 2. Negative 1.37 is going to be at 0.37, negative 1. 0, 1 is going to be at 1, 0. 1 e, which would be up here, is going to be at e1, etc. Okay? And so this curve is going to be rising. It'll be to the right of the y-axis, and it'll be curling outward and upward towards the right there into quadrant 1. This horizontal asymptote that was on the graph of the exponential is now going to become a vertical asymptote on the graph of the logarithm. Remember that a feature of a logarithmic curve is that there will always be a vertical asymptote. Okay. Now, y equals the ln of x and y equals e to the x are inverses of each other. I've got the line y equal x drawn to show that these two curves are symmetric to that diagonal line there, and that will always happen when you have a function and its inverse on the same picture. Those two curves will always be symmetric to the line y equal x. Now, in the previous video, we had graphed y equal log base 2 of x. Okay, so you've already got this in the notes. And I had mentioned that whenever you want to graph any logarithmic curve, you have to first know the corresponding exponential and then switch all the coordinates. So like that's how I had to get the graph of y equal log base 2 of x. I had to first graph y equal 2 to the x, switch all the coordinates, and that's going to give me this curve here. Okay. If I want to graph y equal log base 5 of x, I have to first know the graph of y equal 5 to the x, since that's the inverse, and then I switch all the coordinates, and that's going to allow me to get the graph of y equal log base 5 of x. If I want to graph y equal the ln of x, I have to first graph the inverse, which is y equal e to the x, switch all the coordinates, and that's how I'm getting this logarithmic curve. So in general, whenever you want to graph a logarithm, you have to first know the graph of the exponential and then switch all the coordinates. Now I had mentioned back in section 5.3 that y equals e to the x is the most common exponential function. What I meant by that is that you're going to have significantly more calculations and mathematical formulas where the base is base e than any other base. Okay, like base e is going to come up more than base 2, more than base 3, more than base 5. More than any other base, we will see base e. All right, so with that said, what we could also take away from this is that y equal the ln of x is the most common logarithm. In other words, you're going to have significantly more mathematical calculations and formulas where the base is base e than any other base. Okay, so you're going to have more logarithmic calculations where you're working with base e rather than like base 2 or base 5 or base 43 or any other base. Base e is going to come up the most. Okay, yeah, we'll stop right here.